Hi students, today we'll solve a very interesting problem, and this question, this this is 100% kind. I won't say 100. It is like 90% probability that the question will be solved wrongly, or many students won't get the answer. So you first read the question, then you pause the video, and you try to solve it. If you can't, then you do watch the solution. Let us go through the question. So what the question is? The question is saying that this is a vertical ring. Okay, now you have a string, an ideal string, and here is a bead. So this bead can smoothly, the surface is smooth, so this bead can move easily, okay, throughout the circumference. And this is the center, and this is the radius, and this angle is theta. The question is claiming that even though the surface is smooth, the bead is not going to move. The bead has mass small m, and the bead is at rest. So because this string is there, so there is some tension in the string, because the string is obviously tight, it is not loose, so there will be tension. So what you have to find out is the tension in the string. Let us now go for the solution. See, this bead on the circular path is at rest. That means the motion of this bead is 0. There is no motion. And how can you stop motion in physics? By applying which law you can stop the motion? That is Newton's first law. That means the net forces on this bead must be 0 for this bead to be at rest. Okay. Now motion is along what line? Is it along radius? Is it along tangent? The concept says that the motion is always along the tangent, right? So the motion of this bead must be along the tangent. But because there is no motion, this means that if I draw the tangent here, the net forces along this tangent must be balanced. So let us try to resolve the forces along the tangent. So first, free body diagram, will cut the string. So there is tension, right? Then there is mg, and then there is normal reaction. So all these forces now have to be resolved along the tangent. Now if this angle is theta, then this angle will also be theta. So this angle is 2 theta, sum of interior angle equal to exterior angle. So if I elongate this line, the radius, this angle is 2 theta. So what is the component of mg along the tangent? The component of mg along the tangent is mg sine 2 theta. What is the component of normal reaction along the tangent? Obviously 0, because the normal reaction is perpendicular to the tangent. And what is the component of the tension along the tangent? It is the T sine theta. Now for this bead to be at rest along this vertical ring, the tangential force must be balanced. So if we balance the force, we get the equation T sine theta is equal to mg sine 2 theta. Now resolve sine 2 theta as 2 sine theta cos theta, and you cancel the sine theta. So you get the answer of T as T is equal to how much? T is coming as 2 mg cos theta. So this is the tension that is acting along the string. So if you have tried this question and you got the answer, you are in that 1% category where students can solve this question. Now we'll try another question. Question is saying that there is a spring, an ideal spring, and there is a block of mass small m. The question is saying what is the maximum elongation of the spring. So many students will do here what? They will think that the maximum elongation occurs where the net force on the block will be 0. So what they will do is that they will take the force as kx, and this is equal to mg, the vertically downward force, and they will balance these two forces. So if you balance the forces, you get x equal to how much? You get x equal to mg by k, and this will be in the option, and many students will think that this is the answer. But this is not the answer, because see, a block and a spring, this block performs what? SHM. So in case of SHM, if mg is equal to kx, that means the net force is how much in this situation? It is 0. And in SHM, where the net force becomes 0, that means the acceleration becomes 0. It is a mean position. So this means what you got the x here is basically this x, which is the distance of the body being at rest, and here the acceleration being 0. So in SHA, wherever the velocity is 0, that is the amplitude and this is the mean position. So basically you got this as what? This is the amplitude. But you know that in SHM, the block will further go down from mean position by the same amount of x. That means the total elongation of the spring or the maximum elongation of this spring is going to be how much? It is going to be twice of this value. So the answer is x max is 2 mg by k. Okay, so this is the maximum elongation of the spring. There is another way you can solve this question. See here, at the starting point, the velocity is 0. Wherever the maximum elongation, wherever the spring goes to and comes to a halt, the maximum elongation, the last point, at that point, velocity will be how much? The velocity will be 0. That means here it is at rest, it is here at rest. So we can apply work energy theorem. So work energy theorem is saying what? Total work done is equal to change in kinetic energy, kf minus ki. Now what is the final kinetic energy? It is 0. What is the initial kinetic energy? Is also 0. Now work done. See, gravity is acting downward and the spring is obviously getting elongated downward. Let me to solve this by using work energy theorem, I will assume the maximum distance as x naught and I will try to solve this x naught. So what I am assuming here is that this is the x naught, the maximum elongation, right? So what is the work done by gravity? Mg downward and x naught is also downward. So the maximum work done will be here is mg x naught. And what is the work done by the spring? Spring always does the negative work because the displacement and the force are in the opposite direction, right? So here is minus half k x naught square. You do the side change and you get x naught as 2 mg divided by k. So this is the maximum elongation of the spring. So I hope you really liked the solution.